Tangent planes and linear approximations. I call this one of the collection sections because it collects a few very much related topics into one section, but it's not terribly long or terribly difficult. Just like you can draw an equation, or you can find an equation for a tangent line. So let's say you had a parabola, and you wanted to find the equation for a line tangent at a given point. You would do what? You would find the derivative, and then use that point and the slope that you came up with from the derivative to find the equation for the tangent line. From there, you could also find a linear approximation. You could figure out if I move this amount in the x direction, how much does it change in the y direction to approximate how much the curve changes by moving a certain amount in the x direction, how much does it change in the y direction? Well, in 3 dimensions, instead of having tangent lines, you have tangent planes. In the PowerPoint, I go through the whole process of how to come up with the equation for a tangent plane. It involves gradients, it involves dot products, and direction vectors and all that. And when you get done, you end up with something that looks like this, where you have a surface whose equation you've written as f of x, y, z equals 0, and then you've taken partial derivatives. So you've taken the partial derivative with respect to x, with respect to y, and with respect to z. Essentially, those things are the vector that's normal to the plane, and they determine the slope. So in 2 dimensions, you would call this slope. In 3 dimensions, you're talking about a normal vector that helps to determine the orientation of that plane. Where are you going to evaluate it? You're going to evaluate it at a point. So this ABC is a point. And so just like in 2 dimensions, we have x minus the x coordinate and y minus the y coordinate, except now we also have z minus the z coordinate. So we'll do this defined this way, and then we'll define it explicitly as z is a function of x and y. All right, let's take a look at an example as to what I'm going to do with this. Well, first of all, here's what a tangent plane looks like, and there's other examples that are in the notes. But here you have an almost conical shape region, and then you have a tangent plane at a certain point. Just remember that you need 3 coordinates to determine where that tangent plane is attached to the surface. So it touches it just at that point and then moves on, much like a line that's tangent to a curve. So here's my example. I've got a surface, x squared plus y to the third plus z to the fourth equals 2. I'd like the equation of the plane tangent to that surface at the given point 1, 0, 1. So the first thing is I need the gradient of f. So the gradient of f is going to be the partial derivatives of that x squared y to the third z to the fourth. So take the partial derivative with respect to x, and you only get the first term, right? You get 2x. The y to the third, the z to the fourth, those are both treated as constants. Their derivative is 0. Now take the derivative with respect to y. Well, now the first and the third one cut out, and it's just the 3y squared that goes in the middle piece, derived with respect to z, and now you see the pattern. I end up with a 4z to the third. Okay. Now, evaluate that gradient at the point that I was given, which is 1, 0, 1. So the first line that I wrote up there is the gradient just in terms of x, y, z. Now in terms of 1, 0, 1, well, 2 times 1 is 2. 3 times 0 is 0. 4 times 1 is 4. Okay. So that will give me information about my slopes. Now take those 3 coordinates and let's write the equation for the line. So I'm going to write out 2, which is my first slope, times x minus 1, plus 0, which is my second slope, times y minus 0, plus 4, which is my third slope, times z minus 1. What do I put on the other side? Equals 0. I could simplify this. This looks like not a terrible one to simplify. I'll get 2x minus 2. Everything in the middle drops out. I get a 4z minus 4 equals 0. So if I add a 6 to both sides, I get 2x plus 4z equals 6, or x plus 2z equals 3. So that's the equation of the plane that's tangent to that surface at a given point. Now, remember in Calc 1 you could figure out horizontal tangents. So if you had a nice little parabola and you wanted to figure out the place where the tangent was horizontal, it would look like that. Basically, you would take the first derivative, take that slope, and set the slope equal to 0. Well, how about a tangent plane that's horizontal? If a plane is horizontal, then the normal vector goes straight up out of the plane. So the normal vector is just what we call 0, 0, c. right? 0, 0, and then it's just that third point of that vector that will have any value because that's the k direction. That's the one that goes up. So, using the last example, find the points where the tangent plane is horizontal. Just as a reminder, I'll put the gradient up here. The gradient we came up with was 2x 3y squared 4z to the third. And I want this gradient to equal 0, 0, c. Okay, what do I know? Well, if 2x is equal to 0, then x is 0, right? So if 2x is equal to 0, x is 0. If 3y squared is equal to 0, then y must be 0. Now, put that back into the original equation. The original equation was x squared plus y to the third plus z to the fourth is equal to 2. So I already know that whatever point it is, the first two coordinates are going to be 0. It's just that third one that I've got to figure out. So now let's put a 0 in for x, put a 0 in for y, and we get z to the fourth is equal to 2. Well, when I take the fourth root of both sides, I'm going to end up with z equals plus minus the fourth root of 2. So there's actually 2 points in here. One of them being 0, 0, fourth root of 2, the other being 0, 0, negative fourth root of 2. All right, so those are the 2 points where the tangent plane is horizontal. Okay, just like you can do horizontal tangents in 2 dimensions, you can do horizontal tangents in 3 dimensions. All right, let's take a look at it written in explicit form. Before we had everything set equal to 0, that was implicit form. Now we can write it in explicit form as z equals f of x, y. In other words, as f of x, y, z, we didn't say that z was dependent on x and y, but it turns out it is. How do we do that? Well, I said you can rewrite it as z minus f of x, y equals 0, and now instead of your points becoming like a, b, c, they become a, b, and then f of a, b. That third point now we're writing, yes, this is dependent on those 2 previous points. So now we have a slightly different looking function that gives us the equation for the tangent plane, except this time instead of being set equal to 0, it's set equal to z. So we've got our partial x with respect to a and b, partial with respect to y evaluated at a and b, and then the third thing that's there is that point f of a, b. All right, how does this work? Let's take a look. Let's bring up this example over here. The equation for the plane tangent to z equals the natural log of 1 plus xy at 1, 2, ln 3. How does this work? Well, the first thing is I need some partial derivatives. So I need a partial derivative with respect to x and a partial with respect to y. No partial with respect to z because this is defined explicitly. So the partial derivative of f with respect to x, well, how do I derive a natural log? I do 1 over the inside times the derivative of the inside. Well, the derivative of the inside is going to be 0 plus. Now, when I'm deriving with respect to x, the derivative of xy with respect to x is just that y, right? I'm treating y as a constant, x is the variable, so if I'm deriving xy, the derivative is just y. So I end up with y over 1 plus xy. I'll bet you the derivative with respect to y is not much different. I still start with a 1 over 1 plus xy times the derivative of the inside. Now, if y is the variable, then x is the constant. That's what goes up on top. So that gives me x over 1 plus xy. Now I need to put in some numbers. So now let's find the partial derivative with respect to x evaluated at the point 1, 2. So now I put a 2 in for y, and if I put 1 times 2 down the bottom here, 1 times 2 is 2, plus 1 is 3. So the partial derivative evaluated at 1, 2 for x's is 2/3. The partial y at 1, 2 is going to be 1 over, not surprisingly, the denominator is the same because the denominator is the same as the line above it. So I get a third. Right, how does that formula work now? That formula says that z equals the partial with respect to x times x minus the x coordinate, which in this case is 1, plus the partial with respect to y times y minus the y coordinate, plus f of AB. Well, where would I find f of AB? That's this guy here. This is f of AB. So f of AB is the natural log of 3. If you're not convinced, throw the 1 and the 2 in here, and you'll get 1 times 2 is 2, plus 1 is 3. Z is the natural log of 3. All right, you could go and you could distribute things out. I am just going to leave it here with a nice big box around it. There you go. There's my answer. All right, from here then, let's talk a little bit about linear approximations. Remember in 2 dimensions, you had the idea that if you moved a certain amount in one direction, you could approximate the value for that curve or whatever you were working on, because basically what you had is you had a tangent line, right? So you had a curve, and then you made this thing we called a linear approximation at a point. Well, that linear approximation looks suspiciously like a tangent line, and then you could use that line to evaluate the value of the function for moving a little bit in one direction or a little bit in the other direction. Well, instead of it being a tangent line, now in 3 dimensions, it's a tangent plane. And when you look at that, just like linear approximations in 2 dimensions were basically point-slope form for a line, then linear approximations in 3 dimensions are the equation for the plane that we just came up with. So that linear approximation tells me I can evaluate the actual function by looking at a plane that's very, very close to the function, and maybe the plane will be easier to evaluate than the function. All right, let's try an example and see how this works. So my example is this. I've got some surface, 12 minus 4x squared minus 8y squared. I want the linear approximation at negative 1, 4, and I want to use it to evaluate the function very close to negative 1, 4. Now, it turns out that in this case, we can actually calculate the value. We would do an approximation if we couldn't calculate the value, but here we can actually calculate the value, so we can actually, at the end, come up with the relative error and see how close we were. So let's come over to the side here, because this is going to take a little space. I'm going to write out my problem. So my problem is this. I've got f of xy equals 12 minus 4x squared minus 8y squared, and I want a linear approximation at negative 1, 4. Okay, let's do that first, and then we'll throw some numbers in. First thing I need are some partial derivatives. So the partial derivative of f with respect to x is going to be what? The first and the last terms will just give me zeros. The middle term will give me a negative 8x. The partial with respect to y will knock out the first term and the second term. The third term is just negative 16y. All right, now let's evaluate it at negative 1, 4. So the partial with respect to x at negative 1, 4, well, only the first term counts. There is no y value. Negative 8 times negative 1, positive 8. Partial with respect to y evaluated at that same point. Now this time the first term doesn't matter. It's the second one. So negative 16 times 4 is going to be negative 64. The other thing that I need is I need to find my f of AB. So f of negative 1, 4 means take that and put it back into the original function. So I get 12 minus 4 times a negative 1 squared minus 8 times 4 squared. So I get 12. Remember, negative 1 squared is 1. So that's negative 4 times 1. And then 4 squared is 16. If I do 16 times 8, I get 128. So minus 128. Ooh. 12 minus 4 is 8. 8 minus 128 is negative 120. So that's my f of AB. All right, let's throw it into the formula. So my formula says what? The linear approximation in terms of x and y is the partial with respect to x times x minus a negative 1 plus the partial with respect to y times y minus 4 and then minus 120, because there's my f of AB. All right, so partial x, x minus the x coordinate, partial y, y minus the y coordinate, plus z, which happens to be negative. Let's work this through and try to simplify it a little bit. I get 8x plus 8 minus 64y plus, and then 128, double that, you get 256 minus 120. So that gives me the linear approximation is 8x minus 64y, and now combine like terms together, and you end up with plus 144. Okay, there's my linear approximation. Now let's use that for something. Let's use that to evaluate the linear approximation at negative 1.05, 3.95. So I'm going to put a negative 1.05 in here. I'm going to put a 3.95 in here. And when I do that, here's what I come up with. Negative 117.2. That's my approximation. That if I move 5 units to the left and 0.05 units to the left and 0.05 units down, the new z value will be negative 117.2. Now, it turns out that I can calculate the actual value. Because I know the original function and I have all the information, it's relatively easy to calculate, I can find the actual value. So the actual value is found by putting negative 1.05 and 3.95 back into the original function, right? So for the actual value, we're going to use the original function. Okay, let's do it. The original function was 12 minus 4 times x squared. Well, instead of x, I'm going to write negative 1.05. And then minus 8 times y squared. Y is 3.95. Okay, I already ran through the calculations of this. If you believe me, I came up with, to 2 decimal places, negative 117.23. So this is the actual value. Now, it might be interesting to find the error and to find the relative error. Well, the actual error is not big, right? The actual error is going to be 0.03. It's the difference between negative 117.2 and negative 117.23. What is it? It's 0.03. It's off by not much at all. Now, if you want the relative error, right? So sometimes we call this the absolute error. The relative error is going to be take 0.03 and divide it by 117.23. When we talk about error, we usually talk about absolute values. In other words, it doesn't matter to me whether you're that much above or that much below, just how far off are you. So I'm not worried about negative signs here. When I divide this, I get a small number. I get 0.00026, which means I'm off by only 0.026%. What is that? That's not much, right? That's hundredths of a percent. Percent out of 100, so I move it over, and I'm talking about hundredths of a percent. So not even anywhere near a whole percent. That's a pretty good approximation. It's also pretty close to that point. If I had moved much further away from that point, then the approximations would not be as good. All right, so let's take a look at one more concept, and that is differentials. Differentials talk about change. So those dx's and dy's and dz's now that you see are differentials. They tell me if I move a certain amount in the x direction and a certain amount in the y direction, what changes in the z direction. If you want a picture of that, so this is the formula, by the way. The differential of z is, here we go again, partial f derivative with respect to x of ab, partial y. And then you also notice you've got those dx's and dy's. Those are the differentials in the x direction and the y direction. So moving this much in the x direction and this much in the y direction will change the z direction by how much. So it's the same concept from Calc 1, except now with an extra dimension. Let's take a look at a simple example, and then we'll look at an application, and that'll be it. All right, so approximate the change from negative 1.2 to negative 1.05, 1.9 for that function. So the first thing is, let's find partial derivatives. The partial derivative of f with respect to x is going to be negative 2x. That's it, right? The other two things are treated as constants. The partial with respect to y is just 6y. So now let's evaluate the partial with respect to x at negative 1, 2. Right. What happens when I put a negative 1 in for x? Negative 2 times negative 1 is 2. Partial with respect to y at negative 1, 2 is going to be 12. Now, what else do I know? I was given some other information in the problem. If I'm going from negative 1 to negative 1.05, this thing is moving in the x direction to the left by 0.05. So the change in x is going to be negative 0.05. It's moving to the left 0.05. What are the y's doing? The y's are moving from 2 to 1.9, so they're also going down. So the change in y is negative 0.1. So now all I have to do is throw it in my formula. dz equals f of xy, which is at 2, or I'm sorry, the partial with respect to x at ab, which is 2, times the rate of change with respect to x, which is negative 0.05, plus the partial y, which is 12, times the change in y, which is negative 0.1. Right, when I do that, this will give me a negative 0.1. That will give me a negative 1.2. So to the left, 1.2 plus 1 more gives me to the left 1.3. So as the x's go down by 0.05 and the y's go down by 1/10, the z values are going down by approximately 1.3. That's my differential. Tells me how much things change for values very close to the value that I had. So how is this useful? Let's take a look at one application here. Application for the volume of a cone. Volume of a cone, in case you don't remember, pi r squared h over 3, or 1/3 pi r squared h, however you decide to write it. Suppose r changes from 6.5 to 6.6. So the radius is increasing just a little bit. The height is decreasing just a little bit. So the radius is changing by positive 0.1, right? It's going from 6.5 to 6.6. The height is changing negative 0.05. Right? Height's going down, volume's going up. How much does that change the volume approximately? So maybe I don't want to run through all the calculations. Let's find the partial derivative of the function with respect to r. So let's treat h as a constant. The others are already constants. The 2 drops down in front, so I get 2 pi h over 3. The partial with respect to height is going to keep the pi r squared. Well, that's your constant. Height is to the first power, so I'll get a pi r squared over 3. Now evaluate it at the points that you were given. So the partial with respect to r evaluated at 6.5, 4.2. So 6.5 is the original radius. 4.2 is the original height. When I do that, I keep my pi over 3 and multiply it by 54.6. That's what it looks like. So I'll end up with pi over 3 times 54.6. The partial with respect to h evaluated at 6.5, 4.2 is going to be pi over 3, and then I ran the calculations in the second part. The 4.2 squared over 3 gives me 42.25. Well, the change in volume is going to be a combination of two things. The change in volume is going to be how much the volume changes with respect to r times the change in r, plus the partial with respect to h times the change in h. So the partial with respect to r, I may have to move this up a little bit. There we go. Partial with respect to r, we said was pi over 3 times 54.6. The change in r, up at the top, we said was 0.01, so that's positive. And then the second piece, the h, we're going to pull from the top. So pi over 3 times 42.25 And then the change in h, we said, was negative 0.05. Take those values and add them together. I threw them on my calculator, and I ended up with 3.505. Do we have units? What kind of units do we have in this problem? I didn't put any units in there. Let's just call them units. This is what? This is the change in volume. So the volume increases by that amount. The height decreases, the radius increases, and overall the volume increases because the volume is more dependent on the radius than it is on the height, right? The r is squared in there. So the radius has a bigger impact on the volume than the height does. So the height goes down a little bit, the radius goes up more, and it has a bigger impact in the formula. So overall, we estimate that the volume increases by about 3.5 units. And that's the end of this section.